Alright, so today we're going to discuss the Fundamental Theorem of Calculus. Now, so far, what we've been looking at are we've looked at limits, derivatives, and integrals. And we've used limits in both derivatives and integrals. So the big ideas in calculus are those derivatives and integrals. Two different men, Leibniz and Newton, independently discovered that there's a connection between finding the derivative and the integral. Really, just that they're inverse operations. Now, the big thing with the fundamental theorem of calculus, and there's two parts to it. The first part says that given a function, given that f represents a rate at which the function big F is changing, that is, little f of x is equal to the derivative of big F, then the integral of little f with respect to x from a to b represents a total net change in big F on the interval from a to b. Now, if a function is continuous on a closed interval, we say f is an antiderivative of big F is the antiderivative of little f on that interval. And we've looked at different ways of writing this. With the fundamental theorem of calculus, once we find big F, the way we can evaluate the integral is just to take big F of b and big F of a. If we like, we can also use little g's. I'm not too worried about that. So in other words, we could say that the definite integral is really just equal to the total change, or the displacement, in the antiderivative of f over that interval. And this is just called the fundamental theorem of calculus, part 1, or also known as the evaluation theorem. Now we can write when we apply this fundamental theorem of calculus, we're going to use the notation below. So let's actually now get into some examples. Our first example is the total change concepts and explaining an integral in real-world terms. So we say if f represents the rate at which your 401k changes in value over the month of January, then the units of f of t are represented by dollars per day. And I'm just going to write that as a $sign over day. And dt represents the number of days, and f of t dt represents just dollars, meaning that the integral from 1 to 31 of f of d dt represents the total change in the value of your 401k in dollars for the month of January. Now, looking at example 1, part B, we have if R of t represents the rate at which your pizza changes temperature in a 475-degree pizza oven 5 minutes after the pizza was had been placed into the oven to cook, we say that the integral from 5 to 20 of R of t with respect to t represents the total change in temperature of the pizza in degrees Fahrenheit from 5 minutes to 20 minutes. So then in part C of example 1, you and your friends are planning to buy a ticket to your favorite music group, the Newtons. Everyone wants to hear their latest hit. Why integrate? If A of t represents the rate at which students are arriving at the ticket window, and P of t represents the rate at which they buy their tickets and enter the concert, then the integral from 1 to 5 of a of t with respect to t represents the number of students, and I'm going to just write some stuff in shorthand, number of students arriving to get in line on the interval 1 to 5 minutes. And I can't really write a less than or equal to on my keyboard, so I write a less than and an equal sign. Then here in part 2, the integral from 1 to 5 of pt with respect to t, it's going to represent the number of students, again, that have bought a ticket and leave the line on the interval from 1 to 5 minutes. Now AT minus PT, that's going to represent the rate at which the line is growing or shrinking, which means that the integral from 1 to 5 of AT minus PT with respect to t represents the total change in the length of the line in students on the interval 1 to 5 minutes. Now in part D of example 1, I want us to recall that velocity represents, or VT representing velocity, where there's a positive direction and it's to the right. Now, velocity is a rate at which the position is changing. And the integral from 5 to 50 of v of t with respect to t represents the total change in position on the interval from 5 to 50 units, which has a special name in math, which we call displacement. Likewise, a of t is the rate at which the velocity is changing. Remember, a of t represents the acceleration. So now in example 2, we're going to find the value of some definite integrals by using this evaluation theorem that we looked at on the first page. So we've got the integral from 1 to 3 of x cubed with respect to x. We're going to first write the integral of x cubed. So we're going to write x, we increase the power by 1, so x to the 4th, and we divide by that new power, 4. Now we're going to write this with a 1 and a 3 following it, which means what we're going to do is write this as 3 to the 4th minus 1 to the 4th divided by 4. So 3 to the 4th, 3 times 3 times 3 times 3 is 81. 1 to the 4th is 1, so we're going to have 81 minus 1 divided by 4, which is 80 divided by 4, which is just going to give us 20. So the area under x cubed from 1 to 3 is going to give us 20. Now let's look at b. From 1 to 2, we're going to find the area of x squared minus 3 with respect to x. So first we're going to write x squared as x cubed, increase the power by 1, divide by that new power, minus 3, we have to put an x on that, from 1 to 2. So we're going to take f of b, so f of 2, we're going to go 2 cubed divided by 3 minus 3 times 2, and then we're going to subtract from that f of a. So 1 cubed over 3 minus 3 times 1. Well, 2 cubed is 8, so we're going to end up with 8 over 3 minus 3 times 2 is 6 minus 1/3 minus 3. So we're going to distribute this minus sign into the parentheses. We'll have 8/3 minus 6 minus 1/3 plus 3, which means we're going to have 7/3 minus 3. Now I'm going to rewrite that 3 so we can combine them as something over 3. So I'm going to have 7/3 minus 9/3, which is going to give us negative 2/3. So our answer to B is going to be negative 2/3, or 0.6 repeating if you're using a calculator. Now let's look at a few more. So here we've got C and D from example 2. Let's look at C first. So I'm going to, when I'm finding the integral here, rewrite this as 3. So from 1 to 4 of 3 times x to the half with respect to x. So I'm going to increase that 1/2 by 1. So I'm going to have 3x to the 3/2. And this time, instead of dividing by 3 over 2, I'm going to multiply by the reciprocal. So I'm going to divide by 2 by 3, and I'm going to multiply by 2. When I do that, the 3's cancel out, and we're going to have 2x to the 3/2 from 1 to 4. So we're going to go 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. Now remember, the 3/2 there just means we cube 4 and then take the square root, or we can do the square root and then cube it. I like that second method. So the square root of 4 is 2, and 2 cubed is 8. So we're going to have 2 times 8 minus 2. Well, the square root of 1 is 1, and 1 cubed is 1. So 2 times 1. 2 times 8 we know is 16, minus 2 times 1 is 2, which means this integral is going to give us an answer of 14. Let's look at D. So I know that the integral for secant squared is tangent. So we're going to have tangent x from 0 to pi over 4. So if I find the tangent of pi over 4 and subtract the tangent of 0, I should be able to get my answer. So tangent of pi over 4 is 1 minus tangent of 0 is 0, which means the answer here is going to be 1. So now let's look at E and F. We've got 2x minus 1 squared from negative 1 to 1. So I'm actually going to first expand the 2x minus 1 squared. That's going to give us 4x squared minus 4x plus 1, which means when we're taking the derivative of all that, we're going to have 4x cubed divided by 3 minus 4x squared divided by 2 is just going to give us minus 2x squared plus x from negative 1 to 1. So let's plug both of those in. We're going to go 4 times 1 cubed minus over 3 minus 2 times 1 squared plus 1. And then from that we're going to subtract 4 times negative 1 cubed over 3 minus 2 times negative 1 squared plus negative 1. Well, 1 cubed is 1, so we're going to have 4/3 minus 2 plus 1 minus negative 1 cubed is negative 1, so negative 4/3 minus 2 minus 1. Now I'm going to combine things that I know I can combine. So I can combine this negative 2 and 1 and this negative 2 minus 1. So I'm going to have 4/3 minus 1 minus negative 4/3 minus 3. Now I'm going to distribute this minus sign. So I'm going to have 4/3 minus 1 plus 4/3 plus 3. So I'm going to have 8/3, 4/3 plus 4/3 plus 2, 8/3 plus 2, which plus 2 is like a 6/3. So 8/3 plus 6/3 gives us 14/3. Okay, now let's look at f. So I know when I'm taking the derivative of sine x, not derivative, the integral of sine x, I'm going to get negative cosine x. So I'm going to end up with negative cosine x plus x from 0 to pi. So now I'm going to just plug those values in. I'm going to have negative cosine of pi plus pi minus negative cosine of 0 plus 0. Well, I know the cosine of pi is negative 1, so if I have the opposite of that, I've got 1 plus pi minus the cosine of 0 is 1, so I'm going to have negative 1 plus 0. So I'm going to have 1 plus pi plus 1, which means I'm going to just have 2 plus pi. And I can leave my answer as just 2 plus pi in this case, or even pi plus 2. Now I'm going to skip G and H in our note packet, and we'll continue this lesson in our next video.